Section 3.1, Extrema on an interval. So at this point, we've learned the differentiation rules, and we are in a good position to pursue the application of differentiation in some depth. One of the most important application of differential calculus are what's called optimization problems. So in which we are required to find the optimal or the best way of doing something. For example, minimizing the cost for a company, or maximizing the area that you need to fence, or somehow find the best possible outcome of a given situation. So all these problems require us to talk about maximum, minimum for a given function. Let's put some terminology in place. Let's go to the first definition mentioned here. It goes like this. So let C be a number and the domain of the function f, labeled as capital D. Then f of C is called the absolute maximum or global maximum value of f on that domain, provided f of C dominates all the images through f for any number given from the domain. So f of C is the largest value f can reach throughout its domain. And absolute minimum or global minimum is defined the same way, but it has to be dominated by all other values that f can have. Okay. So let's take a look at this picture. Look at A here. Probably this is the value of f at A. That value, that depth, is the lowest the function f can take throughout its domain. In this particular picture, the domain is A all the way to this point. Let's say it's Z or something. Okay, so f of A is the lowest it can reach, or the function can reach. So at A the minimum occurs. So you have a global minimum or absolute minimum, and at D the function reaches its maximum. So f of D is the absolute maximum of the function. Okay, because that's the highest the function it can reach throughout the domain. Again, the domain is here A all the way to the first coordinate of this point. Okay, so back to the definition. Maximum and minimum values of f are referred to as extreme values or extrema, as the title suggests. All right, we can also talk about relative or local minimum maximum. For example, here B, this is the discussion in blue here. For example, in B, even though this height is not the largest the function can reach, but within its neighborhood, you can think about the neighborhood of B. Let's talk about the neighborhood of B to be AC. Within that neighborhood, that height, this height here, is the largest the function can reach. Such a value is referred to as a local maximum. And similarly for C or E, f of C and f of E are local minimum because in a neighborhood of C, for example, think about BD as this interval. BD is a neighborhood of C. Throughout this interval, f of C is the lowest value the function can reach. So it's going to be referred to as the local minimum. Similarly for E. Okay, so this is the discussion here. You can read it on your own. So this is the formal definition. The number f of C is called a local or a relative maximum of f of C, provided f of C dominates all the values that f can take within that neighborhood of C. And similarly, we call local minimum so C is called local minimum, or f of C is called local minimum, if f of C is the lowest value that the function can take in a neighborhood of C. Let's take an example. So the cosine function, let f of x be cosine of x. This function takes on its local and absolute maximum value of 1 infinitely many times. 1 is the largest number that the function can reach, right? This is the global maximum of the function cosine x. Because any value, any output through the function cosine is between -1 and 1. And that 1 is reached infinitely many times. Precisely, it's reached when the input is an even multiple of pi, right? If you input in cosine 2k pi, where k is any integer, that output is going to be 1. And if you input in cosine an odd multiple of pi, the output is going to be -1. So also the minimum value is attained infinitely many times. Okay. By the way, any absolute maximum is in particular a local maximum, right? So absolute is like a stronger notion than being local. And similarly, any absolute minimum is certainly a local minimum. Okay, I mean, this is based on the couple definitions that we just talked about before. The squaring function, f of x equals x squared, f of x is at least f of 0 for all x. F of 0 is 0 in this case. And that's going to be, as such, this is going to be the absolute minimum value of f. And since it's an absolute minimum, it's going to be a local minimum. And this, pictorially, this corresponds to the vertex of the parabola located at the origin. The function obviously doesn't have a largest number it reaches, or the absolute maximum, because this function blows up at plus and minus infinity. The function x cubed, if you remember, the function x cubed looked like this. So something like this, right? It blows up at infinity, blows down at minus infinity. So this function has neither an absolute maximum nor an absolute minimum. It doesn't even have a local extremum. All right, so we've seen in the previous examples some functions which have extreme values and some others which do not. For example, x cubed doesn't have an extreme value. The following conditions, the next theorem, which is the extreme value theorem, is going to guarantee the existence of extrema. So let's read the details. If we have a function that's continuous on a closed and bounded interval AB, so AB is a closed and bounded set, then the function is going to attain an absolute maximum somewhere, let's say at C, and an absolute minimum somewhere, let's say at D, where C and D are elements in the set AB. Okay, so even though absolute extrema do not exist all the time, but for those functions which are continuous on a closed and bounded set, they're guaranteed to occur. Okay. All right, so let's take a look at this function here. This is a continuous function between the first coordinate of this point and the first coordinate in this point. This is the bounded set AB, right? AB. So that exists somewhere between A and B. That exists somewhere in between those two. The function reaches its maximum and reaches its global minimum. Likewise here, this is another example. That's the point A and that's the point B. This is a bounded and closed set, and the function is continuous. So somewhere it's going to reach an absolute maximum, and it's going to reach an absolute minimum. In this case, that's the C and that's the D and the theorem before. For this function, this is also a compact. This is also a closed and bounded set, and the maximum is attained twice this time, at this C1 and at this C2, and the absolute minimum is attained at D. So this theorem, the extreme value theorem, tells us that the absolute maximum and the absolute minimum are going to be attained somewhere, but doesn't tell us that they're going to attain one and only one time, right? For example, in this case, we have multiple, the absolute maximum attained a couple of times. So it's about the existence, it's not about how many times. Okay. All right, the extreme value theorem is intuitively very plausible, as I wrote here, but the proof is omitted, and the proof, I think, for those who are going to advanced calculus, upper, probably like graduate school or something, they would see the proof. Okay, so what are the conditions that are required for such a conclusion to occur? And the extreme value theorem, you need continuity, and you need the set AB to be closed and bounded. And these two conditions are overriding assumptions. You cannot drop any of them. If you drop continuity, if you drop continuity and maintain and retain the closedness and boundedness of the set, so this set 0, 2 is bounded and closed, but the function is not continuous this time, so continuity fails, and as such the function has, look at this function, it doesn't have an absolute maximum, right? Even though it does have an absolute minimum, but it doesn't have the absolute maximum doesn't exist, correct? So if the function is not continuous, the conclusion of the extreme value theorem is not gonna be preserved. And if the set AB is not closed anymore, for example, this set is 0, 2 open because the function doesn't have a value at 2. 2 is not part of the domain. This is an example of a function which is continuous on 0, 2 open, but this function doesn't have an absolute maximum. So the extreme value theorem here doesn't apply, but the conclusion of the extreme value theorem fails if closedness fails, right? So if you take away the continuity aspect of the function, then the conclusion of the extreme value theorem is not going to hold. We provide an example. And similarly, if you take the closedness aspect of the function, of the domain of the function, then the conclusion of the extreme value theorem is not going to be attained. Long story short, these are two overriding assumptions. Okay. Let's read this comment here. The extreme value theorem says that a continuous function on a closed bounded interval has a maximum value and a minimum value. This is what we just discussed. But it doesn't tell us how to find these extreme values. We start by looking for local extreme values. Let's see why. Let's consider this function. Take a look at this function. At C and at D, there are local extrema that are taking place. At C, you have a local maximum. At D, you have a local minimum. What can you say about the tangent line at this point? Well, it's flat, right? The tangent line has 0 as its slope. And similarly here, the tangent line has, at D, the tangent line has 0 as slope. And we know that the slope of a tangent line is the derivative of the function at that point. So this means f prime of c and f prime of d should be 0. Correct? So this is at least the feeling that we get. The next theorem, which is Fermat's theorem, is going to tell us that this is true for differentiable functions. Let's see how it reads. If the function has a local maximum or a local minimum, so if you know that the function has a local maximum or a local minimum, and in addition you know that the function is differentiable at c, which means f prime of c exists, then that's gonna follow, which means the derivative of c, the derivative of f at c should be 0. So one more time, what's Fermat's theorem? By the way, Fermat is a proper name. His name is Pierre de Fermat, and I think he lived in the 17th century. So again, what does it say? If you know a priori that the function has a local extremum, so if you know that, then if the function is differentiable f prime at a point c, then f prime of c must be 0. Okay, so if you know that f prime of c exists, then that thing must be 0. So here are a couple of examples that are going to caution us against reading too much into the theorem. And by this we mean we cannot expect to locate extreme values simply by setting f prime of x to be 0 and then solving for x. You cannot just look at those guys, because remember, you can look at those guys as long as f prime of c exists, which means f being differentiable at c. Take a look at this function. F of x equals x cubed. We just graphed it before. F of x equals x cubed. We know that this function, we discussed it before, f of x doesn't have a local maximum nor a local minimum. If you differentiate f at x, this is 3x squared, right? And so it's 0 if and only if x is 0. So what can we say so far? We can say that f prime of 0 is 0. So f prime of 0 is equal to 0. But f has no local maximum nor minimum at 0, as you can see from the graph. Or you can do it algebraically. X cubed is positive for x positive, and x cubed is negative for x negative. Correct? All what this means is that the function, or the curve of the function, y equals x cubed, has a horizontal tangent at the origin. But instead of having a peak there, or a valley, the function is going to just cross that horizontal tangent. So what fails here? Why Fermat's theorem doesn't apply? Well, Fermat's theorem doesn't apply because you don't know a priori that the function has a local maximum or a local minimum, right? Remember, Fermat's theorem operates under two assumptions. If you know that the function has a local extremum, and you know that the function is differentiable at c, then f prime of c is 0. Here we started by, we found that f prime of 0 is 0, so this is verified. However, we don't know that f has a local maximum nor a local minimum. So Fermat's theorem doesn't apply here. In the next example, we're going to violate this. Take the function, the absolute value function. This function has a local maximum, actually a global minimum, sorry, a local and global minimum value at 0. Remember, the absolute value function is the V-shaped function, so at 0 you have a global minimum. But this is not verified at 0. F prime of 0 is not 0, right? F prime of 0 is not 0. because f prime of 0 doesn't exist to begin with. Correct? So the point here is, the point that we're trying to make in these last two examples is that if you want to find the local extrema, don't just look at this, don't just look at where f prime vanishes, right? Because f prime vanished here at a point which is not a local extremum, and also here f prime at this point, which we know that the local or global minimum is going to occur at this point, but f prime of 0 is not 0. It doesn't exist to begin with. Correct? So so we have to be careful how to apply Fermat's theorem. You need these two assumptions together, hand in hand, to be verified in order for us to conclude. Okay. The second to last example, which means this example, demonstrates that even when f prime of c is equal to 0, this is the x cubed case, so f prime of 0 is 0, there need not be a maximum or minimum at this number c. Correct? In other words, the converse of Fermat's theorem doesn't hold true. If this happens, we don't get that we have a local minimum. So the converse, meaning if this holds, then this guy doesn't happen, right? F having a local extremum at the number c. Furthermore, there may be extreme value even if f prime of c doesn't exist, like in the absolute value function case, right? F prime of 0 doesn't exist, but at 0 the function has a global minimum or an extreme value. All right. So what Fermat's theorem suggests, however, that we should at least start looking for extreme values of f at the number c where either this holds or this fails, right? Because if you know that the function has a local extremum, then f prime being differentiable at c forces f prime of c being 0. So if this happens, then this follows, right? So what Fermat's theorem can suggest is that we can at least start by looking at f prime of c being 0, or where the function is not differentiable, where this one fails, right? Where this fails. Because if this doesn't fail, which means f prime of c exists, then those are the guys that are going to give us local minimum or local maximum. But if this one fails, I cannot look at this anymore, so I have to consider those by themselves. Correct? Those numbers have given a special name, and they are called critical numbers. So what's a critical number? A critical number is a number c which has the following property. Either c is in the domain of f, but it's not in the domain of f prime. Remember, the domain of f prime is always a subset of the domain of f, right? We said it in class. Domain of f prime is always sitting inside the domain of f. So if you have a number that belongs to the domain of f but do not belong to the domain of f prime, this number is referred to as a critical number. So the function, this means the function is defined at c, but the function is not differentiable at c. This is what this writing means. So such a number is referred to as a critical number. Or if the function is differentiable at c, which means this fails, but f prime of c is 0, then this is another type of critical numbers. So we have two types of critical numbers. Either the function, that number is part of the domain, but the function is not differentiable there, or the function is differentiable there, but it vanishes there. Okay, so what we're saying is critical numbers are numbers either that force this conclusion to fail, or force this conclusion to hold, right? So this is what we mean. And then we can read Fermat's theorem as follows: if f has a local maximum or a local minimum at C, then C is a critical number. We can read it as follows, as such. So if f has a local maximum or minimum at C, then at that number C must be a critical number, because either f prime of C exists, which forces this, so it's a critical number, or this fails. And if this fails, it's a critical number of type 1, right? The first type, this type. All right, let's take an example. So what I said here, what I said just the last 30 seconds is written here. In terms of critical numbers, Fermat's theorem may be rephrased as follows: if f has a local maximum or minimum at C, then C must be a critical number. All right, let's do this example. Find the critical numbers of f of x equals x to power 3 over 5 times 4 minus x. I'm gonna add a page here. Sorry, just a second. Let me see. Okay, so one more time. So I'm doing this exercise. I'm gonna write it on the next page. Just copy it. So solution of exercise. So we want to find the critical numbers of the function f of x equals x to power 3 over 5 times 4 minus x. Okay, so what do we need to find? We need to find those numbers that are in the domain of the function but not in the domain of f prime, and all those numbers where f prime is differentiable but vanishes there. Okay, so this is what we're going to be doing in this exercise. Okay. Let me change the color. So I wanna find f prime first. I wanna differentiate f prime. You can think about this as a product of two functions of x. The first one is x to power 3 over 5, and the second one is 4 minus x. So this looks like u times v. So you can use the product rule, or you can use a different rule by just multiplying first and then differentiating. So it's really up to you. Let me just use the product rule. So product rule, I need to differentiate one at a time and freeze the other. So 3 over 5 x to power 3 over 5 minus 1 times 4 minus x plus x to power 3 over 5 times the derivative with respect to x of this guy. And the derivative with respect to x of this guy is -1. Okay. And what's 3 over 5 minus 1? Well, 3 over 5 minus 1 is 3 minus 5, which is minus 2 over 5. Okay. So this becomes 3 over 5 x to power minus 2 over 5 4 minus x minus x to power 3 over 5. Okay, and negative in the exponent means reciprocal of that thing, so this means 3 times 4 minus x divided by 5 times x to power 2 over 5 minus x to power 3 over 5. And if we want to do the same denominator, how about we do that? How about the denominator being 5x to power 2 over 5? So 5x to power 2 over 5. I want to multiply upstairs as well. 5x to power 2 over 5. Okay. And what is this? X to power 3 over 5 times x to power 2 over 5. This is product of two exponential expressions with the same base, x. So I'm going to keep the base, and I'm going to add the powers. So the powers are 3 over 5 and 2 over 5. And 3 over 5 plus 2 over 5 is simply 1. So I get x. So this is then equal to 3 times 4 minus x minus, this is x times 5, and the whole thing is divided by 5x to power 2 over 5. Alright, I can still simplify a little bit upstairs. 5x to power 2/5 downstairs, and let's do it quickly. 3 times 4 is 12, and 3 times x is 3x, so minus 3x minus 5x is minus 8x. Okay, so this is f prime of x. That's f prime of x. This looks like second derivative. This is really the first derivative, right? Oops. This is just f prime of x. Alright, just keep it like this. Alright, so what do we want? We want to find the critical numbers of this function. So we want to find if there are numbers in the domain of the function but not in the domain of f prime. What's the domain of this function? This is x to power 3 over 5, which means it's the fifth root of x cubed. Fifth root of x cubed, which is defined for all x. And this is a polynomial defined for all x. Product of two functions defined for all x is still defined for all x. So the domain of f is all real numbers. Correct? The domain of this function is all real numbers. What's the domain of f prime? That's f prime. The domain of f prime is, look, downstairs I have the fifth root of x squared. So x cannot be 0 here, right? The domain of f prime is everything except 0. So at this point we can say since the domain of f is all real numbers and the domain of f prime is all real numbers except 0, we get that 0 is a critical number of type 1. Why? Because 0 is in the domain of f but not in the domain of f prime. One more time. 0 is in the domain of the function but not in the domain of f prime. So it satisfies this criterion, which means that the number 0 is a critical number, as we just said. So we have a number coming from this category, and then the other category for critical numbers are those numbers which allow the function to be differentiable but to vanish. So I want to find where f prime vanishes. Well, f prime vanishes if this ratio vanishes. So, so further, f prime of x is 0 if and only if this quotient is 0. But a quotient is 0 if it exists, which means x is not 0, and when the numerator is 0. So this is the same as saying that 12 minus 8x should be 0. That's the same thing as saying that x is 12 over 8, which means 3 over 2. Okay, so x equals 3 over 2. Very good. So what can you say then? The other critical number, which means of type 2, is 3 over 2. So I'm going to just conclude. Then 3 over 2 is also, just to be very clear, a critical number. Right? So this function has two critical numbers, namely 0 and 3 over 2. Okay. All right. Very good. So now let's read the next comment. Before we read the next comment, let me remind you what the extreme value theorem is. Where is it? It's right here. Let's read it again. If the function is continuous on a closed and bounded interval AB, then the function is guaranteed to have an absolute maximum and an absolute minimum somewhere in that set AB. Correct? So if the function is continuous and continuous on a closed and bounded set AB, then certainly the function is going to have local extrema on that set, right? And these are going to be absolute minimum and absolute maximum. If you put this hand in hand with Fermat's theorem now, what does Fermat's theorem say? Either you can read this or you can read that, right? This one. If the function has a local maximum or local minimum at C, then this is going to occur at the critical number. So how can we put them together? Fermat's theorem and the extreme value theorem. If I give you a function, let's start by the next couple lines here. If I give you the function that's continuous on a closed and bounded interval, what can you say? By the extreme value theorem, you are sure that the absolute maximum and the absolute minimum of that function is going to occur on that interval, right? This is what the extreme value theorem says. So one more time, if you know that if you're given a function that's continuous on a closed and bounded interval, the extreme value theorem guarantees the existence of the absolute maximum and the absolute minimum of that function. All right. So these absolute maximum and absolute minimum, either they are local, and if they are local, they should be, by Fermat's theorem, critical numbers, right? In which case they occur at the critical number by Fermat's theorem, or they occur at the endpoints of the interval. Correct? So if they are absolute maximum and absolute minimum, either they are local, and hence they have to be critical numbers by Fermat's theorem, or they occur at the endpoints of the interval, at A and B, right? All right. So in order to find those guys, what do? We look for all the local ones, and we evaluate the function at the local critical numbers, and then we evaluate the function at the endpoints, and then see which one is the highest it's going to be the absolute maximum, and which one is the lowest among all these entities, it's going to be the absolute minimum. And this discussion is embedded in the three-step procedure and the next page. Remember, this page here is something we just wrote. And this is the three-step process that I was alluding to. And it goes like this. It's referred to first as the closed and bounded interval method. It's very natural, as we just discussed. To find the absolute maximum and absolute minimum values of a continuous function f on a closed and bounded interval ab, which are guaranteed by the extreme value theorem, we evaluate the function. We first find the critical numbers of the function on that set AB, and then we evaluate that function f at these endpoints. And then whichever is the highest is going to be the absolute maximum, and whichever is the lowest among these guys, it's going to be the absolute minimum, right? Let's take an example. Find the absolute maximum and absolute minimum of these two functions on these closed and bounded sets. Let's go for one first. Let me zoom in. Okay, part one. So the function f is x cubed minus 3x squared plus 1, and the closed and bounded set, by the way, closed and bounded sets are also referred to as compact sets, just for you if you're interested. That's why I was mistakenly assuming that it's a common language here. Anyway, so the closed and bounded set here in this context is minus half comma 4, right? So the function is x cubed minus 3x squared plus 1. All right, let's find the critical numbers for f. I know by the extreme value theorem, I know that this function is going to have an absolute maximum and absolute minimum on minus half 4. This is guaranteed. So by the previous discussion, either they are local, and hence by Fermat's theorem they're going to be local, they're going to be critical numbers, or they're going to appear, or they're going to occur at the endpoints. So this is why I'm going to go after these critical numbers. Let's find f prime of x. F prime of x is 3x squared minus 6x plus 0. What's the domain of the function f prime? Where the domain of f prime is all real numbers, right? But f prime exists for all real numbers, and hence it's gonna exist for all numbers that are between minus half and 4. So long story short, the domain of f and the domain of f prime are the same. They are both minus 1 half comma 4, right? So the domain of f and the domain of f prime are the same in this case, and they are both minus half comma 4, right? Why it's important to know that they are the same? Because if they are not the same, then I'm going to have critical numbers coming from they're going to be numbers that I lost once I differentiated, right? That I lost from the domain once I differentiated. So in this context, those two sets are the same, and hence there are no numbers that are critical of this type. So all the critical numbers are going to be only from this type in this context. Okay. All right, let's go back. So the critical numbers in this case, as we said, they're going to be only numbers that allow f prime to be 0. Well, f prime is 0 if and only if 3x squared minus 6x is 0, which means x times 3x minus 6 is 0. You can factor out x, which means x is either 0 or 3x is equal to 6, which means x is 6 over 3, which means 2. Correct? So these are the critical numbers in this case. All right. So local extrema are going to occur at 0 and 2. Now I still need to check the value of the function f at the endpoints and see if any of them is going to be lower than any of the two here, or any of them is going to be higher than any of the two here. Right? This is the three-step process, the closed and bounded interval method that we just discussed. So find all the critical numbers first, evaluate the function at the critical numbers. All right, let's do it now. Let's evaluate f at this critical number and at this critical number. Let's do it in a different color just in order for us to refer to it shortly. What's f of 0? So I'm evaluating f at those critical numbers, 0 and 2. What's f of 0? Well, f of x is this much, f of 0 is 1. And what's f of 2? F of 2 is 2 cubed minus 3 times 2 squared plus 1. All right, what's this number? Let's do it quickly. 8 minus 12. 8 minus 12 is minus 4, plus 1 is minus 3. Okay, so the value of the function 0 is 1. The value of the function at 2 is negative 3. Now we're going to check the value of the function at negative half. If the value of the function at negative half is lower than minus 3, then at minus half the global minimum is going to occur. And if f at minus 1/2 is larger than 1, then the global maximum, which is guaranteed to exist by the extreme value theorem, is going to occur at minus half. Similarly for 4. So let's evaluate now f at negative half. Again, this is the second step in this three-step process. Okay, f of negative half. F of negative half, if you look at the recipe of f, it cubes negative half first. It adds the result to, it subtracts from this 3 times the square of the input. Then it adds 1 to the result. Correct? And this is how much? This is negative 1 over 8 minus 3 over 4 plus 1. Am I correct? One more time, this is minus 1 over 8 minus 3 over 4 plus 1. Okay, same denominator, which is 8. I'm going to have minus 1 minus 6 plus 8. And this is how much? This is 1 over 8. Correct? I did the same denominator here. This is 1 over 8. So f of negative 1 over 2 is 1/8. So at negative 1/2, I'm not going to have a maximum because I didn't exceed the 1. And at negative 1/2, I'm not going to have a minimum because I didn't drop below minus 3. So this function, so the function at this point is not attaining neither a maximum nor a minimum. Let's see at the upper bound 4 what's going to happen. F of 4 is what? Well, f of x f of x is the cube of x, so this is going to be 4 cubed minus 3 times 4 squared plus 1. And this is 4 cubed is 64 minus 3 times 16, which is 48, plus 1. Correct? And 64 minus 48 is 16. 16 plus 1 is 17. Okay, so what can we say? At 4, the value of the function is 17, which is higher than the local maximum. Remember, 1 at 0, this value 1, we had the local maximum. So this says that at this endpoint 4, the function exceeds that local maximum, and hence this is going to be a global maximum over that interval minus half 4. Correct? So what can we say at this point? Let me box the things in red. So that's going to be the local maximum, because sorry, not local, global maximum, because that's the highest value that the function can take over that range minus half 4. The global maximum is 17. And the global minimum is -3. It's going to occur at 2. Right? So this guy is a global minimum. Okay, let's take a look at this function actually on Desmos. Okay, so that's the function. F of x equals x cubed minus 3x squared plus 1. And we had the interval minus half comma 4. Minus half is somewhere here, and 4 is here. So we're restricting it from minus half to 4. And on this interval, just from minus half to 4, as you see, the global minimum occurs at 2, which is the point 2 comma minus 3 as we found before. It occurs at 2, and the global minimum is -3. And the global maximum over that interval minus half comma 4, it's going to occur at 4, obviously. Look at the graph. It's very high at 4, and we know the number is 17, right? Let's actually check it. Oh, it's right there. Oops, where is it? Somewhere here. 4 comma 17, as we found. Correct? All right, let's do the last problem. G of x is x minus 2 sine x. So this is part 2. G of x equals x minus 2 sine x. And this is on 0 to pi. Correct? Let's zoom in now. Okay. So as before, the question is to find the absolute maximum and the absolute minimum on 0 to pi, which are guaranteed to occur again on that interval by the extreme value theorem. Let's find g prime of x. Well, g prime of x is 1 minus 2 cosine of x, right? The derivative of sine is cosine. And this is the domain of this is the same as the domain of g, right? Because this function cosine is defined for all real numbers, in particular for those where the function g was defined, which means between 0 and 2 pi. And as such, the critical numbers are going to just be those which allow the function to vanish, the function g prime to vanish. So let's see where this vanishes. g prime of x is 0 if and only if 1 minus cosine, 2 cosine of x is 0, which is the same as saying cosine of x is 1/2. And since we are looking for points for those x which allow this to happen, those x which are between 0 and 2 pi, well, cosine of x equals 1/2. So cosine is the first coordinate of the terminal point. So I'm looking for, so this is the unit circle, let's say. So the angle, so first coordinate is 1/2. So I'm gonna have two angles, one here and one here, right? Well, what's that guy? Oh, what's this guy? This is one of the remarkable acute angles. Cosine of an acute angle is 1/2. That angle is pi over 3, right? So pi over 3. And this guy, technically it's not this guy. What I meant is the other guy, right? So it's 2 pi minus pi over 3. So it's 2 pi for revolution because the reference angle is pi over 3. So it's, and this angle lives in the fourth quadrant, so it's going to be 2 pi minus pi over 3. And 2 pi minus pi over 3. And 2 pi minus pi over 3 is simply 5 pi over 3, right? So so this is then the same as saying that x is pi over 3 or x is 5 pi over 3. So these are the critical numbers. So these are the critical numbers. Of that function g. So I need to evaluate the function at those critical numbers. So let's plug them in g. G of pi over 3. This is 1 minus 2 times cosine of pi over 3, which is 1 minus 2 times cosine of pi over 3 is 1/2. Sorry, I didn't mean the cosine, I meant the sine, right? So this is not what I want. I want to evaluate g at pi over 3, not g prime. I evaluated g prime by mistake. I want to evaluate g at pi over 3, so I'm going to go here. So pi over 3 minus 2 times sine of pi over 3. This is pi over 3 minus 2 times sine of pi over 3 is square root of 3 over 2. So that's pi over 3 minus square root of 3, which is approximately, if you use your calculator, that's approximate. This is negative, certainly, minus 0.68 or something. Okay. All right. At 5 pi over 3, it's gonna be 5 pi over 3 minus 2 times sine of 5 pi over 3, which is 5 pi over 3 minus 2 times, what's sine 5 pi over 3? Well, 5 pi over 3 is in the fourth quadrant, and this sign is going to be negative. So it's going to be negative square root of 3 over 2. Alright, so this is 5 pi over 3 plus square root of 3, which is approximately 6.97 or something. All right. So what can we say so far? We have a local minimum at pi over 3, and that value is minus 0.68. We have a local maximum at 5 pi over 3, which is 6.97. Now I'm going to evaluate the function g at 0. And if g of 0 is below this, then 0 is going to, at 0, I'm going to have a global minimum. And if it's bigger than this, then at 0, I'm going to have a global maximum. And similar discussion applies for 2 pi. So let's evaluate g at 0. What's g of 0? It's immediate. G at 0 is 0 minus 2 sine 0. Sine of 0 is 0, so this is going to be 0 minus 0. So that's going to be 0. So what can we say? At 0, the function is also 0, but that's not a minimum. That's not a local minimum because the function drops below that number at pi over 3. So pi over 3 up to this point, I can say that it's going to be so far a global minimum, and so far 5 pi over 3 is a global maximum. I still have to check the 2 pi, g of 2 pi. Well, g was x minus 2 sine x, so it's going to be g of 2 pi is going to be 2 pi minus 2 times sine of 2 pi. Sine of 2 pi is 0, so that's going to be 2 pi then. So g of 2 pi is 2 pi, and 2 pi is approximately 6.28. Okay, so 6.28 is still below that number. Hence, the function at 2 pi is not going to have a local minimum, and therefore these local minimum and maximum are at this point global minimum and global maximum, right? So these are the global ones at this point. So this guy is global minimum, because that's the lowest the function reaches at this guy, at pi over 3. And this guy, which is approximately 6.97, is a global maximum. That's what I can say at this point.